ITC, isothermal titration calorimetry. It looks a little different than DSC. I think I did allude to it or maybe show this figure before. Okay, it's a more useful application of calorimetry for studying binding interactions. Okay, so we have in this case two sort of reaction vessels. We have our reference, which just has our solvent, so water, whatever we're running our reaction in. And then we have the actual protein solution. So we have protein in solution, and what we're going to drop in is ligand, okay, at a little amount at a time. Okay? And so what we're interested in here, in addition to KD, would be getting sort of changes in enthalpy off of this reaction, okay? And so you're going to slowly add small aliquots of ligand and wait for equilibrium in between each. You're going to maintain both of these two things at the same temperature. And so in order to do that, this is easy. There's no reaction happening. Nothing's happening here. But as I drop my ligand in, when it binds, I should be able to measure something changing. So what am I actually measuring here off of this instrument? What do I have to do to keep the temperature the same between these two things when the ligand binds to the protein? Is the question, is there heat transfer? When it binds, what do I think change in heat would be? What are the two options for a change in heat for a reaction? I'm either releasing it, exothermic, or I'm taking heat to make that reaction, it's endothermic. You can run reactions that go either way in an ITC vessel, and so then you could get output where you're looking at it, sort of the change in heat needed to keep these two cells at the same temperature, right? And so if the reaction happens and it releases heat, I have to suck some heat out of it to keep them at the same temp. Alternatively, if the reaction requires heat, I'm going to put a little bit more in to, again, keep them at the same temperature. With a ligand binding to a protein, it's most likely going to be an exothermic reaction, releasing heat. But you could run ITC for other stuff, other types of reactions. Okay? So what we're measuring is, again, this heat release. Okay? And we expect it to be, we're forming some new interactions between our ligand and our protein, so we expect heat release to be, releasing heat, I'm sorry. DH is negative. It's a release of heat. Okay. And so this is rate of heat release, what we have over here. This is shown in microcal per second, but this is sort of what your data output would look like on an ITC curve. So these are different time points, and each of these spikes is, of course, for you've dropped in more ligand. Okay? And you're getting these spikes for an exothermic reaction. This is sort of the heat that I had to take out to maintain the temperature. And if you integrate under all of these curves and sum them up, you can get a total change in enthalpy for binding. Okay? These are two separate resources, sort of ITC explained, and then this is a company that's trying to like sell you a calorimeter, but it has a nice little description of how ITC works. I recommend reading both of these. They do a really nice job of explaining sort of the process of ITC, okay? In more detail than the couple-minute version I'm giving. Here, what molar ratio is the concentration of free ligand to free protein, okay? So at the beginning, of course, it's very, very small. There is no free ligand. I haven't put any in, or I'm putting in just a little bit at a time. And then eventually, we get over to this end, there would be no free ligand. All of it has gotten bound up. And if our molar ratio here goes through this point of 1, it indicates this slope in the middle of this curve here of 1 is 1-to-1 binding. Okay? So once again, we can figure out sort of the stoichiometry of our ligand to our protein. Does only one ligand bind that protein? If 2 ligands bind that one protein, we would see 2 as our ratio there. I won't talk about this in detail. Box 12.2 in your book goes through getting this total change in enthalpy off of your ITC data in more detail. We have heat flow, how to relate that to change in enthalpy of binding with both the volume of the overall cell, here's the volume of our reaction vessel, and the change in the concentration of our complex. I'll just leave it for you to review. Questions about ITC will again be, hey, look at this plot. Is this exothermic or endothermic? Can you tell if the stoichiometry is 1-to-1 or not from this graph? Like, more broad interpretation. I won't make you do any calculations with ITC. But once you have delta H, you can get delta S, you can get delta G, you can get all the other stuff you want to know. Okay. So this is another figure from your book that has a bunch of statin molecules. I cut the slides where we actually talk about any of the statins on this. I don't know how to say this, but this is Lipitor. So that's probably one everybody's heard of or seen commercials for. This publication here is actually the original raw data that your book made this plot from. Okay, so this is where they got it from, and so they did ITC in a bunch of different statin drugs and looked at changes in enthalpy, entropy, and free energy for all of the different drugs. What's going on here for this fluvastatin or whatever? How come there's no delta H? What do you think the paper reports for that? Any ideas? So everything has sort of some limitations on it in terms of our instrumentation. Their little report was that it was an unmeasurable amount of change in heat that we couldn't capture with our instrument. We've decided it's approximately 0, meaning that all change to free energy is exclusively entropy driven, and that was their conclusion. So this lets you see, like if you look at these relative size of the bars, you can think about the binding of those two things. What is the greater contributor to delta G? Is this an enthalpy driven or entropy driven reaction?